Hello everyone. Welcome to this video on transition diagrams for lexical analysis. Today we will look at a tool or a technique by which we can create lexical analyzers. So as we have seen earlier, the tokens of a programming language can be represented by using our regular expressions. Okay, so regular expressions. So in this example, you can see for the keywords, for certain keywords, I have some regular expressions. For say numbers and identifiers and digits, I have again another set of regular expressions. For relational operators, I have another set of uh, regular expressions. And then last one here, you can see it is WS stands for your white space. So white space basically means more than one of these characters, blanks or tabs or new lines. Okay, so when you have multiple spaces in your program, in your input program, that doesn't have any meaning for the lexical analyzer, or you have multiple empty new lines. So those don't have any significance, and those are not tokens. So you can classify them as white space. So a white space uh, can be represented using uh, this particular regular expression, blank or tab or new line, so one or more. Okay, so given this definitions of tokens and lexemes, okay, we can try to understand this from this given table. So in this table, as you can see, we have three columns. The first one is for the lexemes, the second one is for the token name, and the last one is for the attribute value. So tokens, as you know, it is identified by the token name. We have something like this: token name, comma, attribute. It can be one or more attributes. So here we're looking at only the one attribute. So if it's a white space, WS, then you can see it is not a token, as I have mentioned. Similarly, no attribute values. For the keywords, if then else, you can see that uh, it is not a these are tokens, and their token name is the same as that of the lexeme, but they do not have any attribute values. So if is corresponds to the token if, then corresponds to the token then, and so on. For identifiers, you can see its token name is identifier, and it has a attribute value. And what is this attribute value? It's a pointer to the table entry. So if this identifier is a variable or a method, okay, so this attribute would be a pointer to the symbol table entry where this identifier has been added. Okay, and if it is a numerical constant, then it is token is num. Similarly, here also it's a pointer to the table entry. Now it may not go to the symbol table; it may go to the literal table. Same way, if we have string constants, we have defined string constants, then that string constant will also be pointing to the entry in the literal table. Then if you look at the remaining ones here, these are all relational operators. So they fall under the category or the class of tokens called rel-o. Okay, and what are the attributes? The attribute is the actual operator that corresponds to this particular uh, lexemes. So lt means less than, le means less than or equal, eq means equal, and so on. So these are the attributes for the relational operators, and their token name is rel-o. Okay, so now let us come back to a transition diagram. So as I said, transition diagram, it is an intermediate step in designing a lexical analyzer, and you can think of it to be something like a flow chart. Okay, so it doesn't have the concepts of things of a flow chart, but the idea is the same. So what we can see, let's look at this diagram. Okay, so in this diagram, this is a diagram of a transition diagram. So here you can see there are these circles. Oops. These are the circles here, this one, this one here. So these are called states. If you have already studied a course on uh, your theory of computation, you will know, you will recognize these transition diagrams. So these are the states. So a state in a transition diagram, it will represent whatever input you have already seen between the lexeme begin pointer and the forward pointer. These two pointers we have discussed in the input buffering lecture. So you can go back and check it there. So whatever you have seen between the lexeme begin and the forward pointer is described by the state. So if I am in state 6, say I am here, that means before this I have already seen the symbol or the character greater than. Similarly, if I am at state 7, that means I have already seen greater than, the characters greater than and equal. Okay. So at any point of state, at any state, you will know what you have already seen. So I'll just okay. Uh, let me, so that was about your states. Then you can see this line arrow pointing from one state to another state. This is known as a edge. So it's a directed edge from one state to another state. And it is labeled by a symbol, by one character. So what it means that if I am in state 0 and I have seen the symbol, the next input character is greater than, then I can make a transition from state 0 to state 6. Same way, if I am in state 6 and I have seen the symbol equal to, then I can make a jump to state 7. So that is an edge. Okay. And then you will find that these states 7 and 8, this looks different from the previous two. That's because this has got two circles, concentric circles, and this means that it's a final state. This is a final state. Both 7 and 8 are final state. So final state means it is an accepting state. That means you have identified a valid lexeme and you can now classify it according to the class of tokens to which it belongs. And then here you can see, here you can see the last one here. This has got a star here. Now this means that the star here means retract. I'll just write it here, retract. Retract means move back the forward pointer by one character. So if I can explain it through this diagram. So I'm in start 0. I get greater than symbol. I come to state 6. From state 6, I see equal symbol. I go to state 7. So that means I have found the symbol greater or the lexeme greater or equal to. But after seeing, after reading the first character, I got greater than, I have come to 6. Then from 6, I did not get equal. I got something else. Okay. Suppose I got greater than 4. So I got 4. Now 4 is not equal. So I will come this side. I will move this side. Okay. So that is something else. 4 is something else. So I'm here. Now, which is my lexeme? My lexeme is this greater than symbol. So I have to move back. My forward pointer is here. So I have to come back one step. So retract one step. Okay, so that is the meaning of this star. If I have to retract more than one, then it will show me that many number of stars. So this is a transition diagram. Now, continuing with this, you can see we have something more here. We have, when we reach a final state, okay, we have something like this. So this is you can think of this to be an output of or the return value of a function. If we write the code for this whole thing think of it, writing it in a C program, then when you reach a final state, then you have to return something. So what will you return? you will return that you have seen. Now you are here at state 7 because you have seen the greater than symbol followed by equal. So that means what is this? This is a rel op. So return rel op. So first one is the token. Which token? And then GE. What I have seen, I have greater or equal. So GE is the symbol or the attribute for greater or equal to. So I will return the attribute. So I'll return the attribute. Similarly for 8, that means I have seen greater than and then I have not seen equal, but I have seen something else. So I'm returning again, that's still a relop because greater than is a relop. And what is the attribute? It is GT, which is greater than. So when I reach a final state, I'm going to get something like this. It is giving me what is the token which I have identified and what is its attribute. This is for all the other relational operators. As you can see, we are starting with the start state. Start state is before we have seen any input. So we are starting from here. This is for all the relational operators. So when I see less than, I go to state 1. Then I see equal to, then I go to state 2. Now state 2 is a final state. What should it return? I have seen less than equal to. So it returns rel of LE, less equal. After seeing the first one now, suppose after seeing this symbol, I may get what are the relational operators corresponding to this, and it may be only this, it may be less than or equal to, or it may be not equal to. These three options I have. So I have three transitions here. Okay. So if I see less than equal to, that means this one, I will return this. If I see less than and then the greater than symbol, I see less than, then I get a greater than symbol and I come to state 3. In that case, what is returned? Not equal. And if I see less than and then I get something else which is neither equal nor greater than, then I will, that means I have detected this particular lexeme, so I will return less than. Okay, so this is for less than. Now if it is equal, there is only one. So if 0 is equal, then it returns EQ. If it sees greater than, then I can have again two options, simply only greater than or greater or equal to. So if I see greater than, I go to 6. From 6, if I see equal, I return greater or equal to. If I see anything else, then I return greater than symbol. So this is for your relational operators. This is the transition diagram for relational operators. This one now here, this is for your identifiers. Okay, so we are starting at 9, state 9. I see a letter. Oops. So I see a letter here. Then I move to 10. Then whenever I see any letter or digit, I keep on repeating. I still remain in state 10. Okay. And then I see something else, which is not a letter, not a letter, and mm, not a digit. So I reach the final state 11. And final state 11, you can see there is a star here. That means retract. Retract. Okay. So I will move back the forward pointer by one character so that till I read only the characters. So if I have a variable called sum, okay. So when I see S, so here I'm starting, okay. So I see S. So from 9, I go to 10. Then I'm 9, now I'm in 10. Now I see U, so I'm still in 10. Then I see M. So from 10 again I go to 10 itself. I'm staying here. Then I see, say, equal. Okay. So that is others. So from 10 I go to 11. Now to identify, to get the identifier sum, my forward pointer was here now. So I have to move it back 1. So my lexim begin is here and my uh, forward pointer is here. So between lexim begin and forward, what do I get? I get the identifier sum. Okay. And now what does it return? It returns a function, the output of a function called GetToken, and something else called install ID. Now what are these? GetToken and install IDs are just some functions. What does it return? GetToken, it returns the token identified. So in this case, GetToken will return to me, since I have identified sum. So sum is what? Identifier. So it will return this ID. Then install ID, it returns a pointer to the table entry. So it returns a pointer to the table entry. So somewhere in the symbol table, I will have an entry for sum. Okay. So the pointer to this will be returned. So suppose it is pointing to entry number 10. All right. So this value 10 will be returned. Now, if there is no entry for sum, you are encountering the variable sum for the first time, then it will make an entry and then return the value. So again, if we go back here, sum, it return ID and it will return 10. So install ID will return 10 because 10 is the pointer to the entry in the symbol table for the variable sum. So this is for your uh, for identifiers. Same way you can get also for digits. Okay. So this is quite a complicated transition diagram, as you can see. It covers both uh, numeric, that is integers, as well as your floating point numbers, then and floating point numbers in exponential format. Okay. So all of these will work in this manner. Now, for the RELOP, now let us look at an implementation of it. How are you going to implement this transition diagram? So you think of this as a function. You've written a function in C. Okay. So if you see here, so token, it returns a token, get RELOP. Okay, this is the function. So for the transition diagram we saw in the first in the second series, that is the transition diagram for a RELOP. Okay, so this can be implemented in this manner. So first you are taking the token, then while one repeat. Okay, we have a switch case based on the state. So whichever state it is. So if it is zero, state zero, that means you're starting from zero. You'll notice that the start state is zero for the RELOP transition diagram. So it is reading the next character here in C. Then it is checking if C is less than. If it is less than, it will go to state 1. State is equal to 1. Else if C is equal to, the character you have read is equal to equal, then you go to state 5. Okay. Then if it is not, then you can go to state 6. Okay. You can see this is all the first level. Let me just go back. Let me just go back here. Okay. Let again. I'll just remove all these markers. So what was being done is this part. We had looked at this part. In the first switch case, we are looking if it is this switch for, if start state is 0, then if it is greater, then it will go to 1. If it is equal, then it will go to 5. If it is greater than, then it will go to 6. Then within 1, from 1, now if state is equal to 1, then it will perform all these. It is equal to equal or greater or others. Similarly, if it is state 6, and it will check for these two. Okay. So this is how the implementation is written. So let me put it like this. just clean up this place and then we will come back here. So, so this first level of switch is for the first level of the transition diagram. Then it is checking. If it is 1, then again you will have some more switch cases. And see, in state 8 and in state 4 we are retracting. So in state 8 it is showing this option retract. Retract means, remember, we will move the forward pointer one character back. And what is the what is returned? Ret token means token that is to be returned is greater than return ret token. So you can think of this ret token to be something like a structure, okay? Or you can think, if you have done object oriented programming, you think of it as a class. So it has a thing called, it has a member called attribute. So it is assigning GT because in 8 state 8 it is returned, the function was like this: return, that is state was 8, return rel op, okay, and GT. So that is this is implemented through this, and this had a star, so retract. So this is how you can implement your transition diagram. So you can try this with a small C program, write a small C program to implement the relational operators. You can also try this for your keywords. Okay, so that is all about transition diagrams. Now we'll see in our later classes that transition diagrams you have to write by hand. You have to hard code this whole thing. But there are easier ways to writing a lexical analyzer, because it is not feasible to write lexical analyzers using this method for very large programming languages. So we will see in our next classes how we can use the lex utility to create lexical analyzers automatically without having to write this. But again, from an exam point of view, you have to write your programs. Initially, you have to write lexical analyzers for small languages. For given small specifications, you can write it using transition diagrams.